As she said, my name is John Garretson. I work with Newcomb and Boyd. Who Newcomb and Boyd is, if you don't know. This is a couple years old, so we are actually a 102-year-old business, 1923, out of Atlanta. We have 3 offices now. There's also one in Jacksonville, Florida that's been added within the last year, and all these numbers kind of pump up. Instead of 250, 60 employees, we're about 300 employees or so now, and we are a multidisciplinary firm from MEP. I do acoustics. We have AV, lighting, communications, security, those kind of things. The acoustics team itself is started with Donald Walker, who's our partner in charge, and then a gentleman named Brandon Westergaard and myself run the acoustics group. Right now the group is 8 people deep and has Brandon, who works out of the Twin Cities area, Daniel, who's out of the New Jersey area, and then myself, Joe Hackman, McCall Edwards, Ani, Joe, and Charles are all located in the Atlanta area locally and serve the Southeast region. We participate in ASA, which is the Acoustical Society of America. We are a member of the National Council of Acoustical Consultants, AES, and INS, which is the Institute for Noise Control Engineers. Those are kind of the professional societies that most acoustical consultants join up and follow. So that's a little bit about us. Now, this is a little boilerplate from the AIA for the course. I have to put this on there. This is what tells you what the course is for, what it works for, how it goes, and now is the official beginning of the AIA certified course. So what are our learning objectives today? So we have 5 main learning objectives. We're going to review and understand the general concepts of architectural acoustics. So, and as an acoustical consultant, the 3 things I look at on a typical building are sound isolation, HVAC noise control, and acoustical finish treatments. And that is, sound isolation is how one space is isolated from another space for its acoustics. HVAC noise control is your background noise level generated by your mechanical systems, and finished treatments are your room acoustics treatments like the ceiling tiles that you have in here or acoustical panels. We're going to talk a lot about what single number ratings are, and we're going to, with this presentation, the main focus to understand what single number ratings are and understand what their typical pitfalls are. We're going to understand where the single number ratings come from, where their goals are and how they're best used, and when to look beyond just the single number ratings. We will also look at understanding the general goals of architectural acoustics and sustainable design criteria and how we can help achieve those goals, and then understand what steps design team members can take to better coordinate with acoustical consultants for integrated designs. So first off, what are those single number ratings that we're going to talk a lot about? For airborne sound isolation, we refer to a lot of what we call STC and NIC, and those stand for sound transmission class and noise isolation class, and we'll get into the details of what all those mean later. The single number ratings we're going to talk about for impact isolation are IIC and ISR, impact isolation class, and impact sound reduction. For HVAC noise, here in the US, the most common one we use is NC for noise criteria, and for absorption, the most common one we use is NRC, noise reduction coefficient. So first, some basics. What is sound? How does it work? What is the physics of it? Sound is a pressure wave that moves through air. It is a longitudinal wave, so the direction that the sound is traveling is the same way that the wave is kind of moving back and forth. Because it's a pressure wave, if any of you kind of in the, the old Maxwell tape commercial here, if any of you have ever been to like a live performance or anything like that, if you get close enough to the speakers, you literally can feel the pressure be kind of exerted on your diaphragm and kind of feel it. That is just a pressure wave it is. Sound is frequency dependent, where the frequency is based on the speed of sound divided by the wavelength. And basically, just a general idea of what we want to show you here is there are low sounds and there are high frequency sounds. And the most, the obvious way that most people have to relate to that is kind of like a piano, right? Keys on the left are much lower, keys on the right are higher. As the frequencies get lower, the wavelength goes up. As the frequency gets higher, the wavelength goes down. And 2 of the typical ways that we talk about the level or volume of a sound are dB and dBA. And those are a little bit different, and the difference is what that A stands for. So that's an A-weighted network. And a dB, if someone refers to something as a raw dB, that's typically how a piece of a microphone or electronic equipment might measure that piece of equipment, right? That level as a dB. When we add this A here, that means it's dBA weighted. The A weighting, just like the kind of picture intends, it changes those frequency components to be weighted for how a human hears. We are less sensitive at low frequencies and more sensitive at high frequencies. So if we take a flat measurement at dB, we actually subtract some values at low frequencies, add some values at the other frequencies, and recombine those, and that's kind of the level that you hear it at as a person. dBA is typically for quieter noises, 75 dB and below. When you get up to louder noises and things like that, it doesn't quite work as well. So that's just one of the things that keep track of that. But the dBA is typical for background noise levels and things like that in the built space. So sound isolation, why is it important? Limits distraction. It contains sound and noise, between hotel rooms here. Between hotel rooms, between classrooms and a music space, open office spaces and private offices, healthcare spaces and private offices, recording spaces next to loud spaces. The path that we typically look at. So airborne and structure-borne are the two types of sound isolation paths that an acoustical consultant will look at. Airborne is me speaking and the noise, the air in the space being excited, and then the walls, blocking that airborne noise. Structure-borne noise is just how it sounds like I'm stomping like this, right? How much do the people below me, above me, and to the side of me actually hear that noise? All of these things are frequency dependent, and that's going to be one of the things that we're really talking about today. Is we have those single number ratings, but when we have such a large variety of frequencies that we have to deal with, how do we take performance that is frequency dependent at low frequencies and high frequencies and all these different frequencies? You hear over 20,000 frequencies. You hear from about 20 hertz to 20,000 hertz. So if we had to give you a metric for every one of those frequencies, it becomes ridiculous and there's just too much information to follow. So we boil these things down into single numbers. So here we go. Let's click through this. So general sound isolation paths, like we talked about below. So STC, that's the first main single number rating. That's a very, very predominant single number rating that is used for sound isolation, airborne noise isolation. If I'm talking here, how much does a person on the other side of that wall hear? How much does a person, if there was a room above me, hear? What STC is, as I said, it's a single number rating. All right, it is intended more for speech frequencies. So first and foremost, what are one of the pitfalls of this? If someone is saying I'm building a band room or a large mechanical room or a room next to a cooling tower or something like that, we have to worry about noise coming through that's low frequency. STC isn't a really good indicator of the final performance that you'll get. It really is intended for speech frequencies. It excludes all the information below 125 hertz. So like I said, highway noise, traffic noise, all that stuff, we really don't look at it as an STC. STC is also a laboratory tested condition. It's not a field rating. Anytime someone says, 55 STC or blank STC, that specifically means that that's a lab tested performance. And how do we do that is we take an acoustical test laboratory and we have a source room which actually takes a microphone that moves around on a track system. It plays a large amount of noise in this room. We have either fixed or moving microphones in this space, and it literally measures just the noise that comes between the two spaces. So we literally take the noise in the source room, subtract the noise we measure in the receiver room, and that gives us what we call a noise reduction, which is an NR. That's not the final step, though. What the final step is to turn those into a transmission loss, which accounts for the receiving room space. So we take our NR, and then to account for the receiving room space, we take a 10 log of the surface area and the total absorption of the receiving room. And what that basically does in a nutshell is it takes out the receiving space from the calculation, right? So if we had a concrete room versus a room that was carpeted everywhere, there'd be a different noise level in the space. We need to back that out so we know what just the wall itself does. So once we do that, we have this curve here at these different performance frequencies. These are the transmission losses that we just talked about in that last category, kind of calculated out here. This is a sample wall. So this is an STC 50 wall. It's a 20 gauge stud, 16 center, 2 layers of jip on both sides, and fiberglass. It's a typical standard STC 50 wall. So once we have these transmission losses, how do we get this single number STC? What we do is we use a standardized curve that's been provided. We're losing battery on this again. That's okay. We provide a standardized curve that we then will curve fit to our data. And what we do is we slide this standardized curve up and down until we either have a maximum deficiency of 8 in one frequency band, or the total of all the deficiencies adds to 32. We read what the 500 hertz band is, and that is our STC. So in this case, it looks like maybe these added up, but it's probably this is an 8 right here, so that's what kind of sets the curve, and we don't move it anymore, and it's a 50. Okay, so why is that important? Here's some other wall assemblies that have similar STCs to that 50. We have an 8-inch hollow CMU wall. That's an STC 49, so very similar to 50, but not quite there, just 1 point off. If we add some gypsum to that 8-inch hollow CMU wall, we go up to an STC 52. here's the wall we just looked at, and then we have a fully grouted 8-inch CMU, and that gets about a 55. So again, single number ratings, right? 49, 52, 50. But when we look at their individual performances, they're drastically different. What we see here is these are the three we just added. And what we'll see is the hollow metal CMU, or the hollow CMU, has an STC of 49. And when we add those layers of JIP to the CMU, we actually get better performance above 200 hertz, but below 200 hertz, the performance drops off from the cavity that we've provided from the gypsum. If we overlook that and compare it to that blue line, that gypsum assembly that we had over here, we'll see that typically, even though we have a 49 as our rating for this black curve and a 50, the blue is technically rated higher, we see that at the low frequencies, the CMU is significantly higher. So that's one of the things I talked about why STC is not great at low frequencies. It gets rid of that data and you don't really see it. And as a single number, it doesn't tell the whole story. In general, an STC that's higher will in general be better. But when they become close to each other or at low frequencies, the performance is really assembly based in itself and really needs to be scrutinized on a third octave or octave band level instead of just a single number rating. Okay, so sound isolation, selection, and pitfalls. So how do you pick a wall, a door, a window, or an assembly? So there are industry standard resources like USG selection tools that you can use out there. Other manufacturers of acoustical clips provide test data. Clark Dietrich, stud manufacturers provide test data. A lot of sound control manufacturers will provide a large assembly of test data that you can look through. There are other traditional methods that we're going to talk about too, like the UL listing that we have here, but you're going to have to be very careful when you use those to check the stud gauge and spacing. Stud gauge and spacing highly affects the final STC you get. A thinner gauge stud spaced farther apart actually prevents more noise. It acts like a spring and there's less contact points, so you actually make sure that if you are picking a stud gauge and spacing from a rated assembly that you match that with your actual construction. It's not just the total layers of gypsum. You need to make sure your insulation is correct. You need to make sure there's any specialty drywall or if it includes resilient gypsum channels. So for example, this is a UL U419 fire rated partition. So is this one down here. This one has a performance of 44, this one has a 54 and a 51. All of these are UL U419 partitions. The fire rating is absolutely the fire rating on a UL listing. The STC rating is more of a convenience that's provided sometimes when it's a single rating that's listed for multiple UL listings. So for example, UL 419 has 49 different assemblies that fall under that. Their STC ranges from 44 to 58. So just because you see a UL rating and that's the UL rating you're using for your assembly, you can't necessarily follow the STC that's listed for it unless you kind of dig down and make sure that that is the correct assembly for that. The other type of acoustical isolation we talked about wasn't airborne, it was structure-borne. And what we call for that is we talk about impact isolation or IIC. IIC is very similar to STC in that we have a curve fitting process that we utilize based on the performance, and we come up with a single number after summarizing all the data. It originally was intended for high heels, hard-soled shoes. It comes around from the 50s when there was a lot more hard flooring finishes and people wore harder-soled shoes. It's still used today in a lot of residential settings, code requirements and things like that, but other things still qualify for IIC criteria. It is also a laboratory-tested metric. And in general, higher IICs, again, are higher performance. What they do for IIC is instead of playing noise in a space, they take what they call a tapping machine. This is an ISO tapping machine. It has 10 hammers that are 50 grams apiece on the bottom of it. So it is a standardized noise source. They all drop from the same distance. And the idea is my tapping machine makes the same impacts as anybody else's. So we all put that in the top of the lab. It taps around. We measure in the space below, again, correct for the absorption and the surface area, and we get what we have. I don't know if that's going to play. Yeah, so there you go. That's kind of what it sounds like. It sounds like someone's tap dancing up there, right? So that taps, so we tap that machine above us, we measure below it, we plot a curve of the noise that we measure, and then we do the curve fitting where we, again, slide it up or down, a total of 32 deficiencies, we stop, or 8 in any one band, we stop, we read it at 500, and that is your IIC. Okay. So how do you pick a flooring ceiling assembly for an IIC? Again, there's industry standards like USG selection guides, there's manufacturer's literature for flooring, or you can ask an acoustical consultant. Same things before with IIC. You have to make sure that you're using a similar floor structure. One of the things that is notorious in the marketing material is you'll find an underlayment provider that says, oh, we can achieve IIC 60, or we can achieve IIC 70. And they'll put that out there and you're like, great, IIC 70, I'll throw it on this. Well, that's with a 10-inch slab and a ceiling that's hung underneath with a plenum that's 2 feet deep and all these other things, right? And you're just going to put it on a raw 6-inch slab kind of thing. So you have to make sure that the structure that you're using matches up between the test data that you're using, or as close as possible, and what you're actually designing to. Let's see what else. So field testing. So far, STC and IIC have been lab-rated tests. Laboratory tests are always going to perform better than a field test, and in the acoustics industry, we don't use the same metrics before that. So when we say STC, like I said, that always means lab. IIC is always lab. In the field, we use what we call ISR for impact insulation, and NIC, noise isolation class, for airborne sound isolation. And those don't take out as much as a background room as you need, but it's more of an accurate prediction on, oh, shoot. It's more of an accurate prediction on the actual noise levels that are in the space. Between the field and the lab, the acoustics industry has a standard of about 5 points, which is acceptable. If I design to a 50 and code says I need to meet 50, or criteria says I need to meet 50, if I test in a lab and I get a 45, we consider that equivalent. And the reason for that is because the lab doesn't have what we call flanking paths. So the lab does a very good job of isolating all the different ways that noise might wrap around the structure, because you're testing just a little slab in a hole. Where in a real world, we have joints and other conditions that are less than ideal for that. So about a 5-point difference is typically allowed. So sound isolation summary. STC and IIC are single number ratings. They are a great place to start. They are going to be what most of your criteria is based around. You're going to get, code's going to say STC 50, IIC 50 for multi-dwelling. FGI is going to list STCs. LEED's going to list STCs. But they don't tell the whole story, so you sometimes need to dig into them a little bit more depending on your specific adjacencies and the criticalness of the space. As we said, STC and IRC are lab ratings. They do not consider the flanking paths that you get in the real world. So we typically get about 5 points or so is understood to be different between what a lab-rated assembly is and what we get in the real world. So besides isolation, we said one of the next things was finishes and room acoustics. So isolation is noise from one space to another. Room acoustics is how the acoustics of the space we're in perform. And so for that, we typically talk about room treatments. So there's 3 types of treatments in general: absorptive, reflective, and diffusive. So just some examples to kind of, we have a sponge, a mirror, and a disco ball. And that kind of, if you think about it, is a good metaphor for those. So the way that absorption works, it literally absorbs just like a sponge. The carpet in here, the ACT in here, when the pressure wave that I'm talking with interacts with it, a certain percentage of it just goes into the carpet, interacts with the carpet, gets turned to a small amount of heat, and never comes out of it. It literally acts like a sponge for sound, right? Reflective materials, such as the gypsum wall or any hard surface, as long as it's a hard enough surface, it's literally just like optics. The angle on is the angle off, and it just bounces, all right? And then we have diffusive materials. And diffusive materials are like the disco ball. They still reflect, but they're designed to scatter sound. Right? So what we typically have here is, most of the time we're talking about absorptive materials for a typical application. When we get into performance spaces or maybe outdoor amphitheaters and things like that, we start talking about reflective spaces. And then when we get into things like other performance spaces or musical studios or recordings and things like that, then we talk about diffusive materials. And if you've ever seen diffuser, they're the things that kind of just have all these different size slots and shapes and everything. They really are just a statistically varied surface, so that different frequencies bounce off at different angles and the sound kind of goes everywhere. But the vast majority of what we look at on a typical building, the vast majority of what we'll look at in healthcare is going to be this absorptive portion right here. So absorptive treatments, so what are they and how do we rate them? So the single number for absorptive treatments is NRC, noise reduction coefficient. And what the sound absorption coefficient is below this, that's an individual octave band sound absorption coefficient. So we measure that just like we measure the SCC in a lab. We measure that by putting a material in a room, in a reverberant chamber. The sound bounces around. We measure how much of that sound gets absorbed by the panel at different frequencies, and then we list those absorption coefficient at the individual octave bands. If we sum 250 hertz, 500 hertz, 1000 hertz, and 2000 hertz, and we take the average of those, that's what an NRC is. Okay? And the pitfall with this, again, with a single number rating, is if we look at here, this is a typical ACT, or this fiberglass panel we have at top, the best performing one. It provides a .8 NRC. Now, the general rule of thumb when you think about absorption coefficients in NRC, you can kind of think of it as a percentage of acoustical energy absorbed. If it's an NRC 50, half of the energy that hits that will bounce back, half will not, right? If it's a NRC 90, about 90% of it will hit and 10% might bounce back. For acoustics, we like to keep it around a .7 or so statistically it's really one bounce and the majority of the noise is gone. But what you'll find out is if we look at this fiberglass panel, it says 0.8. 80% of the acoustics is absorbed. That's pretty good. But when we get into the individual octave bands, we see that at 1000 hertz we get one, and we almost are 100% at 1000 and above. We're close to 80 at 500, but when we get lower than that, we're really not doing much, right? So depending on the application of the space, you may need to scrutinize some of the absorption in the lower frequencies and do some other things to make sure that you're getting the appropriate acoustics for what you intend. So again, it's just to say that the overall arching theme kind of is, similar, equivalent single number ratings aren't always equivalent. 1.8 panel won't look the same as the next .8 panel, right? And they'll all have a different performance dip to them. And in general, again, higher NRCs are better, and it's a laboratory tested application. Okay. So how do they calculate? So what do we do with that absorption? So what we do with that absorption data is we calculate the reverberation time for a space. And the reverberation time is the single number rating that has the closest equivalency to a direct connection to the acoustical comfort and the speech intelligibility of a space. So in general, high reverberation times, like big open swimming pools, Catholic churches, things like that, they're harder for a person to communicate with speech, right? But there's so many reflections building up. What the reverberation time does, it's basically a measure of how long we feel it's going to take a space to decay by 60 dB. Statistically, 60 dB has been shown that you can't, if I give you at 100, by the time we get to 40, you'll say that you can't hear it, it's gone silent. So what this means is I pop a balloon or you clap your hands, you make a noise in a space, how many seconds or fractions of a second does it take for that noise to drop by 60 dB? That's your reverberation time, and you'll find that same criteria. Again, lead, FGI, different criteria will point back to a reverberation time for a space type. The important things to remember about reverberation time are, you don't have to remember this exact equation, obviously, but it is proportional to volume and indirectly proportional to absorption. So the bigger the space, the longer the reverberation time, the more acoustical absorption I add to it, the smaller the reverberation time, and we kind of balance those two things as acoustical consultants. There's a couple different ways to look at RT as well too. There's one called T60, which most people understand is 500 to 1000 hertz, and then there's one called RT average, which is a combination of the same bands from the NRC measurements, 250, 500, 1K, and 2K. So when you're talking about reverberation time, it's also important to know if you're talking average, or if they just list regular RT, or what the actual bandwidth that they're requiring. Certain, for example, certain industries like lead wants 3 bands. Lead wants 250, 500, and 1K for their applications. Most other ones will just take the 500 and 1000. So you just need to make sure that when you're talking reverberation time, you're talking about the right octave bands included for what they want to see. And then just some general RT guidelines to kind of give you an idea of what we're talking about. So if we have a 10,000 cubic foot space, for speech, we'd like to see the reverberation time kind of in that 0.7, 0.8 area ideally. The curve also shows as the volume gets up, there's really not much you can do. You can't really dry it out too much because the volume just really does take over compared to the amount of absorption we can add. And for music spaces, the reverberation time is a little bit higher to support the music and actually present fullness and other things like that. But that's really the difference. We look at, is it a music space? Is it a speech space? And from there we know, based on the volume, around roughly where we want to target that RT. And then we know, we then back in with that data of how much material we need to add to the space. Here are some other just general reverberation time guidelines for spaces. It might be a little harder to see. The main thing here is that this is speech. We have speech and music, and then music, and the general trend is just music is longer reverb times, liver space, the sound bounces around more. Speech support is in the lower, more dead spaces down here, and it's typically in that 0.4 to 1 second or less kind of space. Any space that has a reverb time above a second is going to be where you start to get into difficulties with speech communication, especially at longer distances. And below a second is better. 0.6, 0.7 is pretty ideal for a classroom, office space, conference room, kind of thing like that. Okay. Here's a quick little, this is kind of how we envision reverberation when we think about it and when we model it. Like, this is just a visual to let you know. So basically we have a sound source that goes off in every direction, and every one of these little balls that then interacts and hits that surface and does it back out is energy reduced. So when we place speakers, when we think about speaker positions, or a speaker's location and the absorption we place around it, it's kind of with this idea in mind of, at that point, we're going to go 360 degrees and we're going to have all this energy, and how close to that surface can I absorb? What angles do I need to absorb to make sure that different distances and things are taken care of? The absorptive treatments are varied. There's a lot of different options now. The dirty little secret about this is that a lot of their performance is similar. What you pay for and the price difference is just the aesthetic. So if I put, a lot of these, a typical 1-inch material in our world is going to be about a 0.7, 0.8 in that NRC category. All these materials, from the ACT to this 1-inch to the 1-inch fill they put behind this to the 1-inch fill, all these, they're probably acoustically performing very, very similarly. It's just a matter of the aesthetic. So this is a spray-on application in an open office. We have a classroom conference room that has traditional kind of wall panels, tectum. These are metal panels that are up in, I believe this is a pool area, a wood slat. So the aesthetic is really where the money is, and then it's really just about, is it 1-inch fiberglass behind it? Is it a felt panel that's 1-inch or 2-inch, that kind of thing? Most of the cost is in the look. In the last few years, they've also come out with like combination acoustical treatment. So instead of your panels, like we just saw here, instead of literally here's a panel and a panel and a panel on the wall, there's some companies called Light Art and some other things, Arctura, that have integrated acoustical paneling into light elements, into architectural elements that are kind of almost artistic and things like that. So we're seeing more and more of like this integration on providing the acoustical performance, but not letting you know it's an acoustical product or kind of making it hide and go away. So acoustical finishes summary, we have the noise reduction coefficient. It is the average absorption of 250 hertz, 500 hertz, 1000, and 2000 hertz. It's a single number rating, so it might not be suitable for all music or critical listening applications. But for a typical space, a conference room, an office, NRC is by far the vast majority of what is used to set a criteria. Reverberation time is the actual kind of targeted performance of the space. It's the time it takes sound to decay in the space, 60 dB. It is directly related to the size of the space and the absorptive properties of the surfaces. The reasons that we do reverberation and echo control is it limits distractions, it encourages choir activity, it enhances speech intelligibility, and it allows audio systems to operate at the highest potential. This one right here, allowing audio systems to operate at the highest potential, the more and more we see teleconferencing spaces and telecommunication spaces and teleeducation spaces and those kind of things, reverb time is becoming more and more critical because the microphones and the audio system themselves hear much more sensitively than you. So even though a room might sound good to you as a person, as soon as we start putting mics everywhere, the person on the end of your call might start to hear, I don't know if you've ever been on one of those calls where it just sounds like the person's in a swimming pool and you can kind of hear the noise bounce around, it's hard to hear. So it's more critical for when there's live microphones or recording going on. The final thing we look at for the big three is HVAC background noise. So that's just noise created during the operation of the HVAC. This says HVAC, it's really all building systems. We look at plumbing pumps, we look at piping, we look at electrical generators, noise through windows and things like that. Any building system noise that has some noise level expected that can have data pulled from it, we can do the math on and combine those other elements of isolation and noise control to kind of predict noise levels for that. Why do we track the HVAC and the background noise of the building? It's to limit distractions, to provide an acceptable environment for audio conferencing. It prevents fatigue, and it allows for the inclusion of sound masking. This is something, I don't know how familiar folks are with sound masking, but sound masking has been around for a while now, and some things that people do is they say, well, we don't need sound masking, we'll just pick a tighter diffuser, kind of, we'll make a noisy mechanical system. We don't recommend that because it's kind of out of your control. If you decide to downsize your diffusers to get a little bit more noise to them, and you show up day one, you go, oh, that's a little too loud. Can we turn that down? No. If you put in a sound masking system at 40 dBA, and then the users go, it's a little too loud. Can we turn that down? Yeah, right. So there's a little bit of a control there from it. So where the HVAC background noise criteria comes from. So ASHRAE guidelines are the industry standard that establish noise goals in the built environment. As I said before, in America, the noise goals are typically an NC, noise criteria. It is a calculated or measured single number rating, again, that illustrates the noise levels based on the design of the equipment and the room. This is ASHRAE Chapter 49, and Table 1 in it is literally just a list of spaces with dBA, dBc, but the NC category is right here. So you can see on this, hotel room 30, office building, conference room 30, teleconferencing 25, open office 40, hospitality and clinics, patient room 30, wards 35, operating procedure room 35, corridors, lobbies 40. The other source of NC values and HVAC values that you'll get a lot in healthcare is from FGI standards. They also provide some guidelines that are a little bit more, let's say for the operating rooms and the surgical rooms are a little more achievable. 35 is actually pretty hard to hit in an operating room with all the ventilation requirements and things like that. ASHRAE includes other guidelines to help limit noise. They provide velocity limits based on these NC values. So you can literally go to this table and say, if I need an NC 30, the table will tell you that keep your airflow through an elbow at this velocity to meet that. Example duct layouts, noise control, and such. So here's an NC curve, here's an NC table. So these are the NC curves. They are also similar to dBA. It's not dBA, but it's similar. There's not a 1-to-1. I can't say 40 NC is 40 dBA or 45. There's not a math that I can do it, but in general, they track together, right? Lower kind of lowers each other. It is weighted kind of like dB, so that's why these curves are up here. At lower frequencies, we don't hear as well, right? So we're much less sensitive. At higher frequencies, we are more sensitive. And the way that we read this curve is very simple. We just take the highest point. So here's our NC45, right? The highest curve that we break is this NC45 curve right here. We break it by about a point, so that's an NC46. Now, what's important about this, and we're going to update this slide afterwards. I wish it was on here already. What's important about this is just like I said before about STC50 and STC50 don't necessarily mean the same thing. That's the same thing with the NC. This is driven completely by this one point right here. If we had another system that was right here and then swooped all the way down here and looked completely different, they would both be NC46 because it's all driven just based on that highest point. It's called the tangential method, which means it's a good way in the overall to understand the overall level, but it doesn't provide any qualitative comparison for it. We don't know if it's low and rumbly, if it's high and hissy. We don't know if it's neutral in manner and things like that. So just something to keep in mind that, again, a single number rating isn't always equivalent in acoustics because they combine all these octave bands. So what are the paths we look at for HVAC background noise? So ASHRAE also lists a group of paths. We refer to them as the ASHRAE paths. These list 5 of them. There's actually 8 in total, but these are the most common that we look at. And so when we look at HVAC background noise for a space, we will take, say, a typical office, private office, and in this one, it's got a mechanical wall, so that adds this path, but that's not always there. But what we'll always look at is we look at the supply noise, the noise literally that comes from the unit in through the diffuser. We look at noise that comes from the unit, breaks out the duct before it gets to the diffuser in cases that the duct runs completely overhead. We look at the return path, and we look at structure-borne vibration isolation, and we also look at mechanical room walls and things like that. So obviously, if the space doesn't have a mechanical room adjacency, we don't look at that. But for the spaces that do, we look at all those considerations, and we model up each of those paths individually, and then we sum them at the end. So, for example, if this is an NC30 space, and my supply is designed to NC30, and my return is designed to NC30, and the wall is NC30, when we all put them together, we get well over NC30. So the NC30 goals that are listed are the total rooms final requirements, not from an individual path, which is something to always make sure that, so for me, like if I need an NC30 space, I design the path to 25, right? And then when all those, and then I get 4 or 5 of those summing together, they kind of meet NC30 in the end. Here's an example of those path calculations. So we literally take the mechanical plans and the drawings, we start with the data that the manufacturers provide, and that's why I'm always, sure. Mm-hmm.
If you take that space at NC30,
Mm-hmm.
and that's the design is NC30, then
Yeah.
why isn't it NC30 at the end? You said you would rate it at NC25.
Oh, no, the design path here. So
Yeah.
so let's say these 4 paths led to the same room. I'm going to do some quick math with you too. So in acoustics world, 1 plus 1 is 4. Equal plus equal equals 3 more. Okay, 50 plus 50 is 53. Okay, don't follow it. But just that means if I design, if the space is, if the space is 30, and I design this, right? If I design this path to 30, but both of these paths, right? If I design all these paths to 30, that will be 30 plus 30. Now I'm at 33. 30 plus 30, 33. 33 plus 33, 36. Right? So I don't, to design the room to 30, I have to design these paths to lower than 30. And sometimes we start with kind of the 5-point rule, but really what happens typically on a design is one path is driving it, and we kind of control that as best we can, and the other ones we have to lower and reduce to bring the overall kind of down for it.
So I would think that the design, let's say on is 30. Whatever it takes to get that room 30 is what the design is. Not say I wanted 25 to get 36.
Hey, Kane, it's that cumulative effect. So if you have like 3 pumps in series, they'll all be pumping together.
Yep.
So what they have to do is they have to pick a point and then add to that to get to the 30. So the 25, John, is where you're starting the point for your path, but there's other things hopping on that train.
Yeah.
So when you get to the end, it's 30.
Okay.
Yeah. Yeah, the goal of the design is to get the final room at the target of 30. Okay. So mechanical background noise, limiting noise, more comfort, functional, productive spaces. And this was final noise levels consist of multiple potential noise paths. That's kind of what I talked about, why we have to reduce the individual path rating. And then one of the things, the biggest thing you can do to help your mechanical noise is consider the placement of the mechanical rooms. Direct adjacencies to mechanical rooms are one of the more challenging conditions that we come across. NC, again, single number rating. It's calculated or measured for describing noise levels. It's design goals established by ASHRAE and other guidelines, and the NC curves are based on your sensitivity for human hearing. Some of the sustainable design requirements and some of the places that we get these criteria from for various projects. FGI would be the big one for you guys, healthcare, right? That has all those standards. These are just some sustainable ones that have more criteria. LEED, WELL, Green Globes. The IGCC came out with a new construction code that has, for high performance buildings, that has a whole section on acoustical goals. So we use this a lot when there is no criteria or owner's criteria or any general reference provided beforehand. Living Building Challenge doesn't have acoustical requirements, but you do have to make sure that your acoustical materials meet their sustainability requirements, and then there's Fitwell for residential. Those are the more common sustainability designs, but ASHRAE and FGI are going to be the driving force for you guys, unless there's a campus standard that the owner provides. So how to coordinate with acoustics? What does the design process look like? What's the actual interaction back and forth at a design team member and at the typical phases? So when you coordinate with acoustics, at the SD level, what we typically expect to be provided to us is any owner criteria, any sustainability goals, the general plan, and the space programming at the SD level. From that, what we do is we set your design goals, we create a design narrative that elaborates on those goals and some of the conditions we expect. We try at the SD level collaborate on big ticket items. And what we mean by that is if you put that mechanical room right above a conferencing center or a performance space, it's not just going to be a standard slab. There's going to be a heavier lift there. So we try and get ahead of you and tell you, hey, expect this to be a heavier lift. And then discussion of other deliverables. When we move into DDs, that's when we do most of our actual, I guess, plans and markups, right? So first we would do the report here, tell you all the criteria. When we move into DDs, that's when we start reviewing your documents, marking them up, coordinating that process, taking it down and working with the interior, right? So that's where we give you designs for specific partitions to meet these design goals, finishes to meet the design goals, any shaping or anything that you need like that for performance spaces, 3D modeling like that, and then preliminary HVAC items. So preliminary HVAC items are things like things that we can do before the final design is done. For us to do our calculations, the mechanical systems has to be laid out. Before that, we know there's going to be vibration isolation. We know that we want to limit velocities. We know we're going to keep your grills, registers, and diffusers 5 to 10 points below, all these things. So we share that information early so we can get that incorporated. At CDs, that's when we can really do the mechanical noise calculation designs that I showed you, where we go and do a takeoff of every element and actually do the math on that. More communication with coordination, finalizing doors, door seals, summarizing reports based on the design decisions that have come through. And then in CA, what we need from you guys is really just a timeline, a schedule to keep us in the loop on that. We review all the submittals and RFIs. Typically, an acoustical consultant will review all the submittals and RFIs related to our scope in the project. And then site visits, submittal reviews, RFIs, that's kind of typical. Site visits, we see the same thing on every project, to tell you the truth. We look at bridging across walls, we look at non-seals, we look at the sealing and the caulking around all the walls and the partitions that goes up. We check door bottom seals to make sure they're actuating. We will bring our noise level meter with us, and we will take some background noise measurements to make sure if we targeted 30, that we're close to 30, those kind of things.
Let me ask you this question on that. When you're doing your commissioning, and you come in to a space that was specifically designed to provide the noise attenuation process, and you come and you find out that it doesn't meet it, what typically would y'all require to fix? Would you then require something to be added to the exterior of the wall, or would you require the wall to be torn out and redone?
So there's some things that we have to assume in there first. So many times when we come in and measure, it's complaint driven, right? So many times it's not a question of, it said it was supposed to be 50, but we got 45. If we're already there and someone spent the money to have us take the measurement, someone's already said, hey, this wall's not working right. It really gets into the details and the minutia of the exact problem. Doors are the worst. So doors, we have to troubleshoot. It could be a threshold thing, it could be a frame thing, it could be all this stuff. Walls, we try and have to really scrutinize the base assembly for what it was and think about what could go wrong. Typically with a single stud wall, it's going to be an air tightness thing. They didn't provide sealant, or there's penetration somewhere that didn't fix. Double stud wall, they might have some bridging. So it really depends on the specific application.
But you'll find what that is and then identify it.
Yeah. Now, but sometimes, and there's various ways that can happen. Sometimes it is add another layer of gypsum. Sometimes it is you have to rip out this and put it back this way kind of thing to make it work. It really depends on what's causing the issue. But we try and get ahead of that too. So part of that process that I talked about here is during the CD level, most acoustical consultants will provide you with a series, if you want them, a series of details for junctions, for penetrations, for edge conditions, for those things. And as long as we get all those notes and everything in there, then the contractors typically have a pretty good idea of what's expected.
So in that case, a contractor would be responsible to go back and meet the standard, right?
Correct. If it was in the contract documents, and which is a good point now. This is maybe something that I need to point out a little more. So we are an acoustical consultant. We do not do drawings. Everything, when you work with us, we will provide you deliverables that are reports and recommendations. If you don't put them in your drawings and they don't make it on the contract set, I have no enforcement during CA, and you'd be surprised how many times that happens. So. Yeah, so the big part of what we do is in the CD is not just, we've done the education here, everyone knows what it is, but making sure that the verbiage and the sketches and the drawings and everything as they need are in the actual contract document so it's enforceable. So, yes, sir.
So on the CD part, you see this past 10 years, this of course is a huge deal with sound, adjacent spaces on the CDs. Please, when you're working with your acoustical consultant, when VE's brought to the table, please make sure they don't change your air handlers and that arrangement significantly, because these guys have used what you give them back in DDs with the different thicknesses of the cabinets and all that stuff. We've seen it happen, and it gets VE'd out, and the product we end up with is significantly louder because we don't have the proper internal isolation and so on. So
that's exactly
very,
right.
very critical that those selections hold true. As a matter of fact, on some of the projects, we actually pre-order the equipment so that you know that that's what you're getting to match their sound analysis. The other thing is we're running out of space in our campuses. Adjacency, we finished the project where we had to go across the street to the central energy plant. Well, we had to take readings of the existing sound levels, ambient conditions. They would not give us a permit. We had to agree that when we finish that building, we go back and take the sound readings again with no appreciable increase. So, I mean, this is a huge, huge topic. One project we did down in Midtown Atlanta, there was a set of condominiums right across the street, and our generators were pointing right at, so we had to do, so the sound part of what we do today, to me, is probably the biggest change I've seen in the past 10 years. And it's really good.
But you mentioned there's gonna be some VEs gonna be taking place, and when you do a VE, and you're gonna change a piece of equipment, it goes back through engineering, correct?
What
To
should,
evaluate.
a lot of times our acoustical consultants are either hired by the owner, so I don't want to say, but that communication
No,
is so
So
important.
we need to validate that that's going back through the acoustical.
Yes,
review as well.
absolutely, because we're only as good as the model and the information we give them to put all this together to give us a yield on what we need.
Right, he's exactly correct. So this line up here, this first line is the data from the unit. So we literally get your selections, get that noise data, and that's where we start with. That's our starting point. So if you, like you said, if you swap that equipment out to something louder, all our math and the final selections on how to get it quiet are up in the air, right?
The architect usually selects the sounds, that particular part of it.
We don't have the acoustical folks on every project, is what I'm saying.
Okay.
That's what I'm saying to you guys, it's not always in the request for proposal. So if you're in a sensitive area, and I'll just, because you can tell I'm bleeding here from all this, but the other thing is there are local ordinances which you gotta look at. Because each individual area has, it's okay, after 7 p.m., you can't be over so many dB.
That's very true. So when it comes to acoustics, there's a crossover where we actually get into codes and ordinances for the, right? So because it's exterior noise in many conditions, we're not looking at FGI or LEED or anything else to say, hey, this is how loud your cooling tower can be to your neighbors. You have to look up the county and the city and see if they have a noise ordinance and see what that leads to. And it's not always obvious. And plenty of projects do get bid on the back end where they think they're putting it in and then it gets held up later and we have to come out, take measurements or do something like that. I will say on the note that we talked about this, about changing equipment. So please, if you have an acoustical consultant on, like you said, if there's a VE, let the acoustical consultant know. We can reanalyze, tell you what the damages will be, and then the owner can decide, okay, I'll take 5 more points of loudness if that's really $100,000 cheaper, right? It's their decision. But the other thing that we do to try and get in front of that is, like I said, if it's not in the contract drawings, it doesn't count. So what we do is a little bit different, and a good acoustical consultant should do this, is actually scheduling these values, either specifying or scheduling the noise data for the unit so you have that starting place. So you can instantly see the next selection if it's louder or quieter, or you can provide that information to suppliers so they can say, okay, well, this is the unit that we should substitute to because it also meets the noise levels. So that's one of the things that we do is providing that schedule and that data on there. Yep. Okay, but that is pretty much it. Any other questions, please? Not all at once, not all at once. All righty, thank you.